Assalamu alaikum rahmatullahi wa barakatuh. Welcome to the Structure Mechanics Lab. We are going to discuss today the stress strain test. This is some fundamental principles of the tensile test. The tensile test is the best known test in materials testing. It determines tensile strength, one of the most important properties of a material. Furthermore, it is also possible to determine elongation at fraction as a measurement of the toughness of the material. In the tensile test, monoaxial stress is generated in a material sample. This stress is induced via external loading of the sample in a longitudinal direction via a tensile force. This is then an even distribution of the direct stress in the test cross-section of the sample. In order to determine the strength of the material, the loading of the sample is slowly and continuously increased until it fails. The maximum test force occurring is a measurement of the strength of the material. The so-called tensile strength Rm is calculated from the maximum test force Fb and the initial cross-section A naught of the sample. This is sample stress versus strain curve for a low carbon steel, and this is a ductile material, as you see here, how it is fracturing and the necking, and we have a elastic range and then plastic plateau and then the ultimate strength, as was and the aluminum alloy, it is somehow similar, but there is no plastic plateau. This was discussed in your mechanics lectures. In the brittle material, which is high carbon steel, there's a rupture, and this rupture is seen here. We can see the rupture without plastic deformation because it is high carbon. And this is the stress versus strain curves for some kinds of steel, like pure iron, carbon steel A36, high tensile low alloy steel A992, quenching tempered alloy steel A709. And as it says here, strength is affected by alloying, heat treating and manufacturing process, but stiffness modulus of elasticity is not, as you see here. The modulus of elasticity of all of these kind of steel is the same, but the ultimate strength and the yield strength is different. Now let us go to our machine in the lab. We have this machine in the lab, the universal testing machine. It is hand operated, as you see here. It is hand operated, and it is a versatile bench mounted machine for compressive and tensile testing on different material and structures. A steel frame with 4 columns, 1, 2, 3, 4, supports a hydraulic ram. This is the hydraulic ram here. This is the hydraulic ram. The ram pushes up a loading platform. This is the loading platform. The area above the loading platform is for compression test on a wide range of materials such as wood, brick and mortar, which is this area here. And the space below the platform is for tensile testing, which is this space here. During tests, force sensors measures the load applied by the ram. A digital load meter shows the real-time force and stores the peak force. A digital displacement indicator measures displays the vertical movement of the loading platform or part of the structure under test, which we are going to see now shortly. Now we have the shows the tensile force curve versus elongation. We are going to do something similar to this, and we are going to test a sample of steel similar to this, and we are going to apply a tensile force, and the stress on the cross section is the force divided by the unit area by the area of the cross section. Now here is the simplest way to determine the maximum test force is via maximum pointer on the force display. The tensile test itself, the cross section of the sample is reduced. It is and the actual stresses are considerably higher. Now this is the force digital force acquisition, and in this digital force acquisition we measure the force, we have how much force we are applying, and we are zeroing the force. Now during elongation, we are going to start with a length, a gauge length of 50 millimeter, and we are going to measure the elongation, and we are going to measure the elongation at fracture, which refer to the change in length of the sample compared with its original length L naught, and is calculated using the length LU of the sample after fracturing, and LU minus L naught divided by L naught equal to 100%, and our gauge is going to measure this change. In order to measure the length, two measuring marks are applied on the test bar, 1, 2. After fracture, the two ends of the sample are placed together neatly at the fracture point, and the distance between the two measuring marks are measured. Here is our sample, and we have measured the total sample length, which is 172 millimeter, and we have measured also the diameter, the initial diameter of the sample, with this apparatus. It is 9.75 millimeter. Now we are installing the specimen in the steel clamps to grip the specimen while tensioning. Here we have already installed the gripping system, and we are mounting the sample on the inside the machine, and now we are making sure we are mounting lowering down the upper platform. The upper platform is lowered down by this handle, and now we are holding the sample into position by installing two steel rods. As we are going to see here, we have installed the two steel rods. Now we are setting the sample gauge to measure the sample deflection in millimeter. This is a sample gauge, and here the sample gauge measures the sample deflection by moving the 2 points, this 1, 2, moving the 2 pins by moving the 2 pins tightened on the sample surface. So we are going to tighten this pin and this pin on the sample surface, and the two halves, this part and this part, moves away from each other during the tension. Now we are here mounting the sample gauge on the sample stem and tightening the 2 pins on the sample surface. Here the sample gauge, before setting it at 0, we have put the sample gauge and we have installed it. We have zeroed the sample gauge in this slide. Now we are mounting the external sample gauge on the platform and setting it to 0. This is the external sample gauge, and it is touching the platform, and it is measuring the overall change in length. This is a second way to measure the deformation. Here we are setting the digital load meter. This is the digital load meter at 0. We are zeroing it, and we are connecting the data acquisition system to all sensors, which are the external gauge, specimen gauge, the load cell. Here we are capturing the data from all sensors on the equipment software. On the PC we have here the external gauge and the specimen gauge and the load cell. So we have here the overall extension measured by the external gauge, and the gauge extension here in this cell, in this icon, measuring the gauge on the sample, and the load cell, which we are going to see now. Here at the bottom here, the load F measures the loading on the sample, the tension on the sample. As we see here, we are now start capturing the data from all sensor and testing that we are capturing the data. We have here the external gauge and the specimen gauge 0, 0, as we are putting it on the sample and the load cell. Now we have here the specimen. We are now setting up the graph to measure the sample. We are setting up the graph to measure the sample, and we are setting here the x-axis, which is going to measure the gauge extension, and the y-axis is going to measure the load force. Here is the graph, setting a graph view for the testing progress. The graph to read the change in load versus F versus the change in length. Now we are going to set the time data capture. The data will be recorded every 0.5 seconds continuously, and we are going to hit the start button. We have hit the start button, executing the test by applying the tension load. and the manual through the manual operated gear, and mounting the test progress. And we are now going to monitor the test progress in the graph, on the graph here. See this video. So this is this video shows has shown we have shown in this video the test itself. Now the sample has broken down into two pieces, and we are and here we have measured the final diameter, which was 5.9 meter at failure, uh, and now we are going to measure the specimen diameter. We have the specimen diameter in the beginning was 9.75, and at the end at failure is 5.9. We are going, and then we take the data from this from the system, from the computer. Here I want to explain something about what we are going to measure. We are going to determine the tensile strength. Is also known as the ultimate tensile strength, the load at failure divided by the original cross-section area, where the ultimate tensile, which is the ultimate tensile strength, equal to sigma max equal to P max divided by A naught, and P max is the maximum load recorded, A naught is the original cross-section of the area. And also we are going to determine the yield point, which is the stress at which deformation changes from elastic to plastic behavior. Below the yield point, unloading the specimen means that it returns to its original length. Above the yielding point, permanent plastic deformation has occurred. Y, and it is equal to PYP divided by A naught, where PYP is the load at yield point, and this is before we reach the ultimate strength. And now C, by reassembling the broken specimen, we can also measure the percentage elongation, how much this piece has stretched at failure, which is equal to final length minus L naught divided by L naught times 100%. And also we are going to determine the percentage reduction of area, which which is how much the specimen has nicked or reduced in diameter at the point of failure, which is A percentage equal to A naught, the initial, minus A failure divided by A naught, which is AF cross-sectional area at the site of the fracture. We need you to find these things. We have already performed the test with two different sample of steels. The initial gauge length of the sample is 50 millimeter. The initial diameter is 9.7 millimeter. The final diameter is 5.9 millimeter. So we need you to calculate the percentage elongation, the calculation of percentage reduction of area, determine the ultimate force from data given, determine the tensile yield strength, draw the stress versus strain graph for the two samples, determine the modulus of elasticity for each sample, and put it here in this table, and this is the sample of the data uh, given. We have here the specimen gauge length, the initial specimen diameter, final specimen diameter. It's actually need to be corrected. It is 5.9 millimeter. Anyways, I'm going to give it to you in the corrected manner. Now this is the real data collected from the data acquisition. This is the force, and this is the specimen elongation. This is delta L. This is measured by the gauge delta L, and you have the initial gauge, which is 50 millimeter, and this delta L you add. This is the initial gauge length, 50 millimeter. So what I need to do is to look at how much I have what is the maximum, delta L, and I add this delta L to the initial gauge. This will give me the final length of the gauge. So I have the initial gauge length, and from this column, the gauge extension delta L, I will read at the end the maximum gauge length is, and add it to the initial gauge. Initial gauge length. I will add the gauge extension to the initial gauge length. This will give me the final gauge length, and I will have here. Never mind about the last column here, but focus on this column, the gauge extension delta L. So you have everything. You have the force. From the force and diameter, you can calculate the stress, and you have the gauge length delta L, and you have the original length. You can calculate the strain. Thank you so much for your hearing. Wassalamu alaikum wa rahmatullahi wa barakatuh.